Oh, okay. Thank you. Okay.
Will we start?
Oh,
So it's my enormous pleasure to welcome Amit Deshpande from Microsoft Research to this campus and for this talk. Amit studied theoretical computer science at CMI and then he did his PhD at MIT. He's been with Microsoft Research after graduation since then. His research interests lie in responsible AI, specifically in fixing data bias and plumbing AI ML pipelines. And generally, he's doing very exciting research, and it's a pleasure to listen to him. So, no pressure.
thank you. Thank you for the introduction and thank you for the kind invitation to give a talk here. This is my first visit to Ashoka. So happy to see you all. I will talk about some, even though there is AI ML in the title, what I will be talking about are some of the theoretical questions, mostly like you could even think of them as mathematical questions that I came across while working on problems related to fairness in machine learning. Uh, so my trajectory has been like from math to theoretical computer science to machine learning, and that too in machine learning some fairness and robustness questions. And some of these are also relevant in the context of LLMs, but or the way people think of AI these days. But I will not be talking about those interpretations. These will be sort of simpler questions related to fairness in classification and ranking. So as the title says, randomization, a friend or a foe in fair AI ML. So when people think of randomizations, especially if you think of randomization in algorithmic decision making, some people might think of randomization as a bad thing because randomization can sort of give you, even for two similar individuals or even for the same individuals, if you are taking a random or randomized decision, you might get different decisions at different times. And that can be considered as unfair. But on the other hand, like a coin toss is something that we naturally use to break ties. And we think of it as a fair coin toss is fair, like it's a way of fairly deciding something. So it's also used in a very natural way. Uh, so this is just to tell you about my journey, like how I got into this, like work on fairness, was because I attended a workshop on fairness, accountability, and transparency in machine learning. This was in 2016, I think. So at that time, this was like a small workshop. It was a small community of researchers in computer science, even in other areas like outside of computer science, social sciences, law, and other areas. And the community basically uh, it was a diverse community that wanted to work on fairness, accountability, and transparency because they saw machine learning as something of a threat that it can uh, create, it can change the world in ways that can be unfair to certain demographics and so on. Now it has become a conference, which is a full-fledged ACM conference called ACM Fact. Yes. So at that time, I was working on some questions related to summarizing or selection, uh, where you are given some data points and you have to pick a subsample or some small subset of them. And some of these had uh, constraints about fairness and diversity. And at that time, it looked like a natural sort of venue to publish such results. Now it has become a much wider community. So I just wanted to sort of put this here to tell you that my journey has been through theoretical computer science problems that found applications here. And slowly I started working on fairness in machine learning. So some of you might have heard of this book called as Weapons of Math Destruction by Cathy O'Neil. So this was one of the books that came out around that time, which pointed out issues that happen with algorithmic decision making. And it has like how big data increases inequality and threatens democracy in its title. So that came out around 2016. There was also this ProPublica article series on machine bias, which so there were these software packages that were used in the US about like for recidivism. That is, how likely is it that a person might commit a person who has committed a crime might commit the crime again. And this software actually assigned some kind of a risk score to different individuals. And ProPublica published an article series where they showed that this software was, which was called as Compass, COMPAS. So that Compass had a lot of bias, especially related to gender and race. And the other thing that came out around that time in 2018 was this project called as Gender Shades, which showed that all these face recognition programs, they have a lot of bias in the sense that they have high difference in the accuracy rates for male versus female and darker skinned, uh, fairer skinned people versus darker skinned people. So these were kind of the triggers that made sure that the community finds these problems as important and works on them, tries to uh, come up with abstract formulations that people could work on, try to define metrics for fairness. Oh, this is just accuracy. Yes. So this is the accuracy that some of these different face recognition. So this was actually a gender classifier which looks at an image and tells the gender, and the accuracy for darker male, the accuracy for darker female, lighter female, and this is the gap. So this was published in the Gender Shades paper in 2018. Things have improved since then. Also, some of the companies decided not to sell facial recognition software because of this gender shades. Okay, so the objective of this talk is not to debate on what is fair, because there are multiple definitions of fairness and many of them are incompatible with each other. So I will not be sort of debating about what is fair. I will just take some simple definitions which make sense. You could think of them as like, these are just some metrics that one can take so that one can actually define a problem, formulate a problem, solve the problem. But you could think of these as just like arbitrary choices. You could pick some other definition and maybe ask the same problem and try to solve it. Then the other thing, the takeaway would be that even the simplest mathematical models of fair classification and ranking give non-trivial results. Like you can, when you formulate them and try to solve them, you might observe things that are very interesting. And the third thing, because this talk is about randomization, I would specifically tell you about results that say something about pros and cons of randomization in fair classification and ranking. Okay. Yes. So as I said, what is fairness in AI ML? Like, unfortunately, there is no commonly agreed definition of fairness. But two common kinds of fairness metrics that people study can be sort of, or these are the two categories that you can divide most of the fairness metrics into. One is group fairness, which basically says that you want equal outcomes across demographic groups. So you might want equal accuracy or equal true positive rate, or you can think of any other things. Say in case of ranking, it could be NDCG for two races or two genders. Here, the races, genders need not be two, they can be multiple, but the simplest case would be binary race or binary gender. And the simplest case, again, you could think of it as like binary classification with binary group label. The other notion of fairness is individual fairness, which says that we want similar predictions for individuals who are similar in all the features except the sensitive attributes, where sensitive attributes could mean race or gender. So if two individuals or two data points, they differ on only the sensitive feature but have otherwise very similar features, then the model should not give different predictions on them. And again, this could be on an average. The typical notions of individual fairness would say that you want this on an average, but you could also make it more stricter. So in this talk, I will be focusing on group fairness, and we will see what are the definitions of, there will be a different definition of group fairness for ranking, which may not have equal outcomes, but it is more about representation in the top ranks. But you can still think of it as like equal outcomes, like equal representation in the top few ranks when you rank some items. Yes.
Can we say that if you ensure one, that is
No, not really. So they are incompatible with each other. Okay. So just to motivate like why this is practical, you could think of like binary classification scenario of instant personal loan where you apply for a loan. Like these days, there are these companies that say that, oh, you can apply for an instant personal loan and it gets approved or rejected immediately or very quickly because they are using algorithmic tools to basically assess how credit worthy you are. And now you want these tools to be fair because you don't want unfairness, like you don't want their prediction to be unfair based on, let's say, gender. So let's look at group aware binary classification. So imagine that your data point, I mean, think of it as essentially a feature vector which has D features. These could encode age, income, education, employment, tax returns, and so on. So each data point or each individual, we can think of that as just a feature vector which has D coordinates. The class label is a binary class label. Think of it as like loan approval or rejection. Sensitive attribute also, for simplicity, think of it as binary, like for example, binary gender, male or female. Then the classifier predicts. So classifier takes such an input. It takes the feature vector. It also takes, in this particular case, we will be looking at group aware classifiers in the sense that they take the sensitive attribute also as a part of their input. There is also a notion of group blind classification where the sensitive attribute may be legally prohibited. But many times what happens is there are other features that reveal the gender in some way or the other, or reveal the sensitive attribute in one way or the other, because of which people have found that it's always good. And also, if you want to measure fairness, you would need that you would need to collect the sensitive attribute anyway. So here, for simplicity, we will be looking at group aware binary classification. That is, the classifier takes the non-sensitive features as well as the sensitive attribute as the entire feature vector and then predicts. This f is a classifier and the prediction is f of x comma a, which is done from the training data. And what all these machine learning techniques do is they try to fit f of x comma a to y as best as possible, where on the training data you have the y labels. So it's just trying to fit a model to the data that you have. Yes.
So when you take features, maybe kind of data sets also have gender.
Correct.
The feature vector of them can be gender is already there. That's how we generally train.
Sure, sure.
Now, when you're saying fx comma a equal to y, how is it different from that?
I'm just saying that keep it as a separate coordinate. It has that. That's all. Okay. So now the first thing that you would want from such a classifier is that you want it to have high accuracy. So let's say this capital X, capital A, capital Y, let this be a random data point sampled from a data distribution D, which is a joint distribution on the non-sensitive features, the sensitive attribute and the class label. So there is a joint distribution on these and you sample a random data point from this joint distribution. And the accuracy of your classifier is just the probability that you output the label correctly by using only the X and A. Right? So this is just the accuracy. And now the first question that you would ask is, what is the classifier that maximizes accuracy? And this is well known in the literature, and it is called as the Bayes optimal classifier. So in case of binary classification, you could think of it as conditioned on the sensitive attribute and the features. So conditioned on what these two are, there is a probability that the label is 1. If that probability is more than half, greater than or equal to half, the optimal classifier should assign it label 1. Otherwise, it should assign label 0. And this is kind of intuitive. Int is just indicator. Yes. And this is kind of it looks intuitively true, and you can actually prove it, that conditioned on these features, what is the probability of the label being 1? If that is greater than or equal to half, you would label it 1, otherwise you would label it 0. And this particular quantity, it's called the regressor, or and it's denoted by eta of x comma a, which is just the probability that the label is 1 conditioned on the sensitive as well as non-sensitive features. Uh-huh.
Knowledge of the joint distribution.
Yes. So if correct. So in reality, you don't have the distribution completely. Like you don't have the complete knowledge of the distribution. You get finitely many samples. But even to before going there, this is just to sort of know what the optimal classifier looks like, so that can we even sort of approximate it using the data that we have, and also using the hypothesis class that you have. So in practice, what would happen is you would get finitely many samples from this distribution. You would have a specific hypothesis class, like say linear classifiers, or maybe some decision trees. And you want to find the best one that minimizes error or maximizes accuracy. Right? But before going there, this is just to characterize, can we at least characterize what the optimal classifier looks like, so that we know how far we are from it. So this is the most basic question one would ask. Now the thing is, the same thing can be asked for fairness. So what is group fair binary classification, and what is the analog of the Bayes optimal classifier in fair classification? So here are two notions of fairness. We can sort of look at them as these are also the most popular notions of group fairness. One of them is called demographic parity, or in simple words, it means equal positive rate. So conditioned on the demographic group or this sensitive attribute, so A being 0 or A being 1, the probability that you predict 1, your classifier predicts 1, should be equal. So it has equal positive rate for both the groups. And the other one is, yes, X and A may be correlated in strange ways. Yes. So the other thing is equal opportunity or equal true positive rate, which means that among the positive examples of that group, what is the accuracy? So think of this as accuracy over the positive examples in that group. Or in the context of the loan example, you could think of it as how many credit-worthy individuals from a certain group are assigned or are given loan. So you want the approval rate of credit-worthy individuals from group 0 to be the same as the approval rate of the credit-worthy individuals from group 1.
Normalize for x in some way.
Remove x from the
X in the right manner, kind of. So that
Component of A and X.
correct.
If X is the reason why you're discriminating, then that should not be. That's okay.
Oh, if x you are
X is like who has PhD degree, for example. And suppose men have more PhD degrees. So, for example, then much of these results are coming. You're seeing unfairness just because they actually are. Can we correct for that somehow?
But this definition will not be a problem. Yes. Equal opportunity will not have a problem. Because here you will divide by probability of y equals 1 and a equals 0, right? That will be the denominator. So,
We're not saying that
so
they should have the same rate. All we're saying is the accuracy in both cases should be the same for positive.
correct, correct.
That's the interpretation side, but for you, it's like from a joint distribution, you pick a condition on this, you
Yes,
want your
yes,
to satisfy.
yes,
Still, that's the
yes,
bad side of it.
yes. So this is better than demographic parity. At least it does not have the issue that you pointed out. Data or so you mean the proportion itself in the data would be less, which is not a problem for equal opportunity. Yes, because of this conditional probability. Why is the class label? Why is the class label? A is the group. So these are, you can think of it as like positive examples conditioned on the positive examples from group 0. What is the probability that your classifier labels them, your classifier predicts them as 1 or predicts them as positive? Similarly for this. So that's why I mentioned that in this loan example, this would be conditioned on being credit worthy and belonging to group 0. What is your probability of getting your loan approved? Yes. So if you take these, there are also other similar notions that people look at for group fairness. But one can naturally ask this question, now that we have these notions of group fairness, what is the analog of the Bayes optimal classifier? So before going there, let's also look at what are randomized classifiers in this context, and does randomization help for accuracy? So does it help for accuracy? Does it help for fairness? Both. So all 0, all 1, or Bernoulli, so a random coin toss, a fair random coin toss, all these classifiers are DP and EO fair. They satisfy demographic parity and equal opportunity. On the other hand, if you look at this, so if you look at deterministic classifiers, then the thing is the Bayes optimal classifier is deterministic because it just looks at that eta of x comma a, whether it is greater than or equal to half or less than half. So the Bayes optimal classifier is deterministic, and in fact, you can show that randomized classifiers cannot give any better accuracy. So conditioned on the non-sensitive features and the sensitive attribute or the group, conditioned on those, you can think of it as at every point there is a coin toss that gives you the label according to the joint distribution. And now the best thing that you could do was to put this threshold at half on that probability. And randomization does not give you any better accuracy. So just by using deterministic classifiers, you can get the Bayes optimal classifier, which has the best possible accuracy among all the deterministic classifiers as well as randomized classifiers. And this Bayes optimal classifier need not be DP or EO fair. So because of that, what one would look at is maximizing accuracy subject to some constraints on demographic parity and equal opportunity, where one would trade off accuracy for fairness. So the natural thing that one would do, like one way to define, say, fair Bayes optimal classifier is you want demographic parity or equal opportunity, and among the classifiers that satisfy demographic parity, what is the classifier that maximizes accuracy? Or among all the classifiers that satisfy equal opportunity, what is the classifier that satisfies that maximizes accuracy?
But how do you then characterize? So just things that
Yes.
given the constraint you've given.
Yes, yes. So maximize accuracy subject to group fairness constraint. This could be one constraint could also be multiple constraints, but for simplicity, think of this as just one constraint. Let's say equal opportunity constraint. So among all the classifiers that satisfy equal opportunity, maximize accuracy. Now, there are two things that you could do, whether you do this over all deterministic classifiers or whether you do it over all randomized classifiers. Randomized classifiers will give you slightly larger set of classifiers. But we will get to that later. First, let's, sure. For every point, just do a fair coin toss with probability, which gives 1 and 0 with probability half-half, and that is your prediction. It's a randomized classifier that satisfies equal opportunity, that satisfies demographic parity. It may have very bad accuracy because it just also all zeros and all ones may have very bad accuracy. Yeah. But they are all fair. Bayes optimal classifier, on the other hand, gives you the best possible accuracy, but it need not always be fair. So now the thing is, you want to find something which is in between, and you have the choices to make. Do you want a deterministic classifier, or do you want to also go for, like, do you want to go for randomized classifier? So if you look at the Bayes optimal classifier, there is a way to think of this indicator function. So that when f is actually a binary classifier and y is also a binary class label, you can write it as this algebraic formula. So f times y plus 1 minus f times 1 minus y. So that if both are the same, this evaluates to 1. If they are different, they take different values, then it evaluates to 0. And the probability can be written as expectation of this expression. So basically, the joint distribution on x, a, y, you push the y part of it, y conditioned on x and a, inside. And because we knew that this probability of y equals 1 conditioned on x equals little x and a equals little a was this eta function, you can write it as this expectation. And the same thing can be rewritten as follows, that it's an expectation over the joint distribution on x and a, f, like f of x comma a, that is f times 2 eta minus 1, plus there is a constant term which is just probability of y equals 0, which comes from just the expectation of this 1 minus eta term. Yes. Oh, so eta is, I can go back to the definition, eta is this. Eta of x comma a is this. Probability that y equals 1. Maybe I can write it here so that. Yes. So the nice thing about this is that you can first of all see that why Bayes optimal classifier has that half threshold. So whenever eta is greater than or equal to half, then this will be yes, then this will be positive. Otherwise, this will be negative. And whenever this is negative, you would want to oh wait, no, whenever yes, this you want to maximize accuracy, right? So whenever eta is greater than or equal to half, you would assign f as 1, and otherwise you would assign f as 0. The other nice thing that you can see is that this is a, if you think of x comma a, if you think of f, this is a linear function in f. If we were to think of f as not just a binary, but whatever, if you multiply f with something by a constant, this is a linear function in f, which is going to be important. And now that we can write accuracy like this, you can also I mean, it's a simple exercise that if you want to write, say, true positive rate or true positive rate for a group, that can also be written as an expression like this. So one nice thing is that accuracy is a linear function of f. And even these group fairness constraints that like say demographic parity or equal opportunity, they can also be written as linear functions of f. We will come back to this again when we talk about randomized classifiers and why this plays an important role. But for simplicity, now pretend that the features, the set of features is finite. So there was this x that came from some script x, the set of all features here, and then there was, this was just the set of sensitive attributes. Imagine just for simplicity that this was some finite set. You could write it as 1 to n. Imagine that that's a finite set. Doesn't really matter, but it just sort of helps think about this concretely. Because then you can think of your classifier as just assigning 0, 1 values to these n points. There are n data points, your classifier just assigns 0, 1 values to these data points. And randomized classifiers can be thought of as like a relaxation, where you assign values in the 0, 1 interval instead of assigning values 0, 1. And yes, and then flip a coin with those probabilities. So basically, instead of assigning it 0 or 1, it gives you a probability. You flip a coin with that probability, and that gives you the prediction. And the other thing is that if you look at accuracy of that randomized classifier, you can also write it as this expectation of f, where f is a vector whose coordinates take values in 0 and 1, because all these things are linear. So interestingly, it turns out that accuracy and the fairness constraint, this applies to not just equal opportunity. Here I have written equal opportunity just as an example. This applies to demographic parity. It also applies to many other notions of fairness. And they turn out to be linear in F. So essentially what you are doing is, there is a linear program that gives you the optimal solution. And if you want deterministic fair Bayes optimal classifier, then that is just the integer optimal solution of this program. And if you want randomized fair Bayes optimal classifier, that can be thought of as the optimal solution of the relaxation. Yes. Uh-huh. Uh-huh. Oh, okay. So equal opportunity constraint, it's just yes, difference is 0. And then you can convert it just like we converted the probability into an expectation. You can also convert this difference of probabilities into an expectation. Yes, yes. So it will just be like expectation of a quantity that is linear in F equal to 0. That's a constraint. And if you look at this simple concrete example where you pretend that, say, the set of these sensitive and non-sensitive features together, that is just a finite set. You could think of this as like your classifier just has, yes, these are just the assignments that you have. So it has like capital N variables, and in the integer optimal solution, you assign 0 or 1 values to each of them. And in the relaxation, you assign values that are in the 0, 1 interval to each of its.
So you're saying that relaxation will help.
No, relaxation helps. So I will, yes, I will show you in what way. So it's an n-dimensional vector. each of its coordinate is a real number between 0 and 1.
But f of xa is in 0, 1. So what does it mean for f to be?
Because f of x comma a is like each coordinate. You can think of it as, even though it's a function, you could think of it as like each, the value that it takes at each point as a coordinate. It's like writing down the table of f as a vector. Yes, yes. So now, because a picture is worth 1,000 words or million words, so this is how it looks like. So you could think of your binary classifiers. Your binary classifiers are, so there is this hypercube, the Boolean hypercube, and there is actually this continuous Boolean hypercube. So 0, 1 interval to n. These integer points are actually the binary classifiers because they correspond to the table of predictions that f has at all the inputs. And the points inside this cube in the interior or anything other than these vertices, they are the randomized classifiers. And what we are doing is optimizing a linear objective subject to a linear constraint. So the fairness constraint gives you a linear hyperplane that cuts this hypercube. And now accuracy gives you some linear objective, and you want to find the optimal solution. So now the thing is, if you look at this fairness constraint, it can happen that maybe all zeros, so first of all zeros lies on this, all ones lies on this, the fairness hyperplane. In fact, all the points that join these two vertices, these are all random coin tosses that have the same bias. So for example, if you look at the midpoint of them, that will be the half point. So this is in 3 dimensions, but think of it as like eventually we want this in n dimensions. So the midpoint of these is the Bernoulli half classifier. It just, at every point, it just flips a coin with bias half. The other points that lie on this line are Bernoulli with some fixed bias, p. At every point, you toss a coin with bias p, and that is your prediction. Those are also EO fair and DP fair. So all of those are fair, but there are also other classifiers that satisfy this. And they all form this hyperplane because it's a linear constraint. Fairness is a linear constraint. Accuracy is a linear constraint. Now, the deterministic Bayes optimal classifier is an integer optimal solution from this hyperplane intersected with the cube, but the integer optimal solution. So it may happen that you can cook up distributions where the only fair solutions are all zeros and all ones. So there is no other deterministic solution. So if you want really deterministic classifier that maximizes accuracy subject to equal opportunity, your only options are all zeros and all ones. Whereas if you look at randomized solutions, then it is a vertex of this intersection of the hyperplane with the continuous hypercube. You have other vertices that are also available. So because it's a linear objective, you know that the optimal solution will be a vertex of this polytope that you get by intersecting the hypercube with this fairness constraint and a vertex of that. The other interesting thing that comes out of this is that, and one can actually, so we realized once we could sort of think of this geometrically, one of the things that we could realize that we could also create distributions where this gap can be really large between the accuracy of the fair Bayes, the randomized fair Bayes optimal classifier and the deterministic fair Bayes optimal classifier. And it can be made very large, like as large as half. So that the deterministic Bayes optimal classifier may have accuracy close to half, which is as good as random, whereas the randomized fair Bayes optimal classifier has accuracy like very close to 1. So one can
constraint where you exactly want this fairness to hold.
uh-huh.
If you relax that, then that also moves this hyperplane linearly,
Sure,
right?
yes. So yes, so many of these things also hold when you have your fairness constraint is not exact equal opportunity, but it's a hard constraint, saying that the equal opportunity is at most the equal opportunity difference, which is the difference between the probabilities, is at most epsilon. Yes, but it's still as long as it's a hard constraint, you can still create these kinds of scenarios. You have a fixed bound.
Then it is a linear program.
Yes, yes,
You move towards the
yes,
Bayes optimal.
correct. The yes, then the other interesting thing that comes out is that if you look at this hypercube and if you take this hyperplane where it cuts, the vertices of this object that you get, they will always lie on the boundary in the sense that they will always be on some edge, which means that the optimal randomized fair, the randomized fair Bock or this randomized fair Bayes optimal classifier is actually a convex combination of two deterministic classifiers. And interestingly, these two deterministic classifiers, their predictions differ only on one point. Yes, so you are random only for one data point. Otherwise, you are deterministic. This is when you have only one constraint. If you have k constraints, you can prove a similar thing where you would be randomized only for k data points. Otherwise, you are deterministic. So you don't need too much randomness, but you gain a lot. So if there are these objections that, oh, randomized decisions are bad, we don't want randomized decisions, here is one way to sort of convince people that it's randomized, but not randomized everywhere.
N dimensions?
This is in n dimensions.
When n becomes infinity, the conclusion still holds?
When n becomes infinity, the conclusion will still hold. Yes.
They were saying that the randomization is only in the dimension of the constraint.
Yes.
So you can be deterministic with x.
Yes. So you can have, say, demographic parity and equal opportunity, both constraints. So you want to maximize accuracy over classifiers that satisfy both demographic parity and equal opportunity. Then the thing is, you can show that the randomized fair Bayes optimal classifier can be written as a convex combination of, instead of 2, it will be 3. Yes. So it will be like k plus 1. If there are k constraints, it will be k plus 1. You couldn't do, so in fact, there are these results which, impossibility results which say that you can't satisfy, say, DP and EO both simultaneously by deterministic classifiers. So Klein, this was not known. This part of it appears in, okay, so this appeared in an ICML paper this year. ICML paper is about something else. So the main result of the paper, I will tell you about the main result of the paper also, but the intuition came from this. So this figure is there in the ICML paper, the results are there in the ICML paper, but the title of the ICML paper is something else because it's a result about some other. Yes. So as I said, you can, once you know this thing that, okay, fairness constraint accuracy maximization is just a linear program, you can do lots of things. You can show that there exists data distributions such that the accuracy wise, the randomized fair Bayes optimal classifier is strictly better than the deterministic fair Bayes optimal classifier. And this is the other thing that I told you, that it can be expressed as an ensemble of at most 2 deterministic classifiers. If it is just one fairness constraint, like say equal opportunity. So the ICML paper was actually about something else. It was about, you can actually look at the accuracy of the Bayes optimal classifier is a function of the data distribution. So given a data distribution, you can consider the Bayes optimal classifier on and look at its accuracy as a function of the data distribution. And now if you change the data distribution, how does the accuracy change? Now that we know that the Bayes optimal classifier is a solution of this linear program, its optimal value is the accuracy of the Bayes optimal classifier. The optimal value of that linear program is the accuracy of the optimal classifier. One can actually analyze these kinds of things. So what we studied was a similar question for fair Bayes optimal classifier. So what was known was that the previous results were known for, there was this famous result of Kearns and Lee. I think I forgot an R here, Kearns and Lee. They showed that for any deterministic hypothesis class, the optimal accuracy is Lipschitz in the total variation distance over data distributions. No assumption on the data distribution. And what was known was that there exists deterministic hypothesis classes such that if you try to do the same for accuracy subject to optimal accuracy subject to fairness constraints, then it's not Lipschitz. So the first thing was for any deterministic hypothesis class, whereas I mean this could be like a fixed hypothesis class instead of allowing all deterministic binary classifiers. Right? But it also applies to the, so the first result, it applies also to the Bayes optimal classifier. If you think of your hypothesis class as all binary classifiers, this says that the accuracy of the Bayes optimal classifier is Lipschitz in total variation distance over data distribution. So if you change your data distribution a little bit in total variation distance, the best possible accuracy, that is the accuracy of the Bayes optimal classifier, should not change by much.
So you're concerned about the distribution from which data is being generated?
Yes.
Not the number of data points?
No. The distribution from which the data is being generated. And what was known was that that does not hold if you, although it was not really known for the deterministic fair Bayes optimal classifier, it was known for a particular hypothesis class. So what we showed was that this does not hold for deterministic fair Bayes optimal classifier, that this accuracy is not Lipschitz as expected. But turns out that for the randomized fair Bayes optimal classifier, it's close to Lipschitz. It's what is called as locally Lipschitz. So locally just means that the constant, the Lipschitz constant, depends on the point where you are, if you, yes. So Lipschitz means there is a global constant, so that if you change the argument of your function, the input to your function by delta, your output or the function value is at most L times delta, whereas here that L, the constant, depends on that.
Lipschitz is almost like saying uniform. It's all continuous and stuff.
Yes.
Not anything stronger in that.
So here it's, yes. So here the locally Lipschitz, I mean, take it with a, I mean, what we have is a very strong notion, but it's not exactly Lipschitz. It's Lipschitz in one direction. So actually what we wanted was like Lipschitz in both the directions. We did not have that, but we have it only in one direction. So let me see if I can quickly also tell you about, but this was the result of the ICML paper this year. Yes and no, in the sense that all these things can be done using the linear program, but some of these results for us, the proof is more involved, and it was
more general.
come again.
As in, it's true for like any hypothesis class, not just say this NK.
These are no. What do you?
My point is, if you look at the earlier statement that you
Yes, they were for any.
determinant.
Yes, These are not for any deterministic hypothesis clause.
This is in that capital N diff case.
Yes,
Right.
correct.
So then which
And this proof is not using linear program. Like if you look at our ICML paper, this proof is not using linear program, although you can also write it using that linear program idea. So we chose the other way of writing it because that was easier to explain. There were some proofs that are easier to explain using linear program. These were not easier to explain using the linear program, although you can still prove them. I mean, it gives you a very nice handle that whatever you are trying to do is an optimal value of a linear program.
Does duality help in any way?
No. Although the characterization of optimal fair classifiers use duality, like deterministic fair classifier. So there are previous papers, one by Menon and Williamson, the other is by Elisa Sellis, Nishit Vishnoi, and others. So that they both use duality in a very nice way. They try to characterize deterministic fair Bayes optimal classifier. And just to go back to this, the characterization is very nice in the sense that the deterministic fair Bayes optimal classifier turn out to be threshold classifiers where the threshold is not half. The threshold is input dependent, as in for every x comma a, there is a t of x comma a threshold that gives you the deterministic Bayes optimal classifier. And in fact, if you look at actually here, it turns out that that threshold is also even further simplified for group aware classification. It's a threshold that only depends on group. So on the group. So two groups have two thresholds. So instead of the threshold being half at every point, all the points that come from group 0, so the f star of x comma 0 would have a threshold all for the group 0 points. There will be another threshold for all points from group 1.
When you talk about implementing this,
Uh-huh.
linear programming with
Yes.
NS high is costly.
Yes. So you can't do any of this when you want to. This is all to understand what it looks like. But there are some nice takeaways that you can have. Like for example, we had looked at in a different context, we had looked at how robust these classifiers are. And when you change the distribution, and turns out that all the deterministic, so there are ways to find fair classifiers on a given data. There are fairness toolkits which offer you multiple pre-processing, in-processing, post-processing methods. And it turns out that the ones that give you deterministic classifiers, they perform poorly compared to those that use ensembles. And ensembles are basically a way to get these randomized classifiers, because instead of outputting one classifier, you give a distribution over deterministic classifiers. And it turns out that empirically, when you try to do these things, ensemble methods give you much better fairness accuracy trade-offs and give you much better robustness when you change the distribution.
Yeah, like these idea of flip and all are just illustrated.
Yes. This is just sort of, it gives you some pointers to think about, which you can then apply in practice. So for fair ranking, maybe I can quickly tell you that in fair ranking, the problem is that there is this pairwise preference data that is given. And given that data, you want to rank items. And typically people do this by maximizing log likelihood, in the sense that your data gives you what is this. So there are, say, n items, and your data gives you a probability of preferring item I over j. And you have a model, and that model tells you what is the probability of preferring I over j. This is like a probabilistic preference model. And you want to find the best model that fits the data by doing this, by maximizing the log likelihood. One popular model is this thing called as Bradley-Terry model, where each item has a score, and the probability that the model prefers I over j is e to the si divided by e to the si plus e to the sj.
This is irrespective of people, or people can just then, like, for example, if you want to say how do I prefer something, that can
So
just
the,
be thought of the parameter.
yes, yes. So this is a probabilistic preference model, and the data might not be according to this model. But what you try to do is you try to fit this model to the data by doing maximum log likelihood, and whatever best parameters fit your data, you would SIs. Those will be your scores, and then you sort the items according to SIs. Right? And interestingly, you can also, this came up because there are yes. So this has there are ways to sort of also extend this to something called as placket loose, where you can think of it as giving an ordered list of items. But so the way you would do it is the items have scores S1 to Sn. You pick the first item with probability proportional to e to the score. So e to the, so this is like applying softmax to the scores. That gives you a distribution. You sample one item according to that. Now the thing is, you apply softmax to the scores of the remaining items, which gives you a distribution. You sample the second according to that. Yes, and if you continue like this, it will give you a permutation of the items, which will be like an ordering. And this defines a distribution over all orderings of the items. It also defines a distribution. You can also use it to define distribution over partial incomplete orderings of these items. Right? And
Have these SIs and then you do that, or
so
you already have this list and now want to think of this probabilistically and then we do it in the way you do.
So if you have SIs, you would do this. When you have data, what you do is you find the SIs that best explain your data by just optimizing this function. So in fair ranking, whatever known was earlier was this two kinds of methods, either post-processing, where you have a model that is doing this ranking, that has learned to rank from data. And now you have constraints. The constraints are group fairness constraints, which say that there should be at least some representation of, say, a particular group in the top K ranks. Like, say, I want at least, say, 50% or say at least 40%. If there are two groups, I want each group to have at least 40% representation in the top 10 ranks. So I want to maximize the ranking utility subject to this kind of representation constraint. Or so one way was doing in processing, where you optimize the objective, like say maximum log likelihood objective subject to these kinds of fairness constraints. But there people typically thought of constraints which were also group-wise outcome metrics, like ranking utility. The other was you train a model to maximize ranking utility. So you learn to rank and then change your output ranking a little bit, massage it a little bit to satisfy these constraints in the top few ranks. And both of them, they had this drawback that if you did re-ranking, it was done unaware of what was done as learning to rank. Learning to rank had no fairness. Only re-ranking had these fairness constraints. Or if you did in processing, which was solving this learning to rank objective subject to some fairness constraint, typically that gave only guarantees about fairness in expectation. Your actual output need not be fair. Like, for example, you could have a ranking that with half probability gives all the ranks to men, and with half probability it assigns all the ranks to women, so that with half probability, so in an expected sense it's fair, but each output need not be fair. So one of the things that we did was we sort of gave an end-to-end solution, where the in-processing was aware of the post-processing and the post-processing was aware of the in-processing. So what you do is you sample first a random fair assignments of groups to ranks and then fill them using this Bradley-Terry model.
groups
Yes.
and I want to
Yes.
pair,
So
but that's the problem, right? How do you sample a random pair assignment?
yes. So the random fair assignment, basically there are some upper and lower bounds about how much representation you want. So in say ranks, the simplest thing that we could sort of do is in ranks 1 to 10, I need at least so many men and at most so many men. Like I have uh, upper and lower bounds constraints for say men and women candidates that I am ranking. Similarly, between 10 to 20, there are some constraints. 20 to 30, there are constraints. Now the assignment just says which rank will go to which group. And there are certain assignments of ranks which satisfy these constraints. There are certain assignments that don't satisfy these constraints. Among the group assignments that satisfy these constraints, we want to pick one at uniformly at random. And once we have picked that, the actual item that will go there, that will be done by applying Bradley-Terry within that group.
So you basically just think of it as a
Yes.
feasibility problem.
Yes.
Identify feasible guys and then just
Yes. And if you do this, you can actually solve an end-to-end objective where the training is done with this post-processing. That is, so the training is aware that the objective will have this post-processing incorporated in it. And
loading to rank is a problem that doesn't care about fairness to billing.
correct.
Now, what kind of group fairness are we looking at in this rank? So, just to be clear, the
Yes.
ranking is you're given some preferences,
Yes.
pairwise preferences.
Yes.
And you want to just get a distribution over the ranks of what is an objective ranking. So that's what I
Correct. Correct.
Now, how do you bring in group fairness?
How do you bring?
Just give me an idea of
Yes.
what does that
So
look like?
you want, say, in the 1 to 10 ranks, you want that the number of men and number of women should be at least 4, at most 6, so that it is balanced. Between ranks 10 to 20, the number of men and women should be at least 4, at most 6, or it can also change at least 3, at most 7. So you can have different constraints like this for representations in the ranks. And now you want to satisfy, you want to make sure that whatever randomized ranking that you output, it must satisfy these constraints. So it should not, it doesn't, so there are randomized rankings that may satisfy these constraints in expectation, but we don't want that. We want actually like every ranking that is output by your randomized ranker to satisfy these constraints. Yeah. So among such rankings, you want to maximize ranking utility.
So we start with some ranking randomized ranking. And then do it in condition on this event again. That kind of.
Yes, so that may not work if the number of rankings that satisfy this is very less. So this also had some LP kind of flavor in the sense that essentially like all of this turned out to be sampling integer points from polytopes, because these are the group assignments that satisfy some constraints. And there was other part of it which was not related to LP. This is like you can actually write down this kind of objective subject to this probabilistic preference model that is fair, and you can actually compute its gradients efficiently, and you can optimize it efficiently. So that was part of this SIG-IR paper. The nice thing was that in both of these cases, so let me just conclude that randomness can actually improve accuracy, fairness, robustness, and we could use randomness in classification and ranking in a very nice way, which was like theoretically interesting, and it also gave us some insights about how to use these things in practice. Like for example, using ensembles for fair classification was one way to do it, and also in case of fair these fairness, many times the like say deterministic rankings cannot give, say the topmost rank cannot be assigned to two groups, but randomized rankings can do that. So this was also useful in many applications. And in fact, randomness can also be thought of as a computational resource in reasoning, where you can actually think of more randomness as allowing you to do a random walk. And whenever you want to sort of do things in a memory constrained way, randomness is useful, which is some recent work where it turned out that randomness was also useful for other problems. So I just wanted to point this out, that there are different ways to think about some number of positions. For internships, they vary over time, yes, from year to year. Sorry for going over time.
Fairness algorithms, does anybody use them anywhere?
Which ones?
All these
Oh, so
fairness algorithms, are they
oh, class of fairness
given
algorithms.
attraction that would
So LinkedIn uses them. There are also, I mean, in terms of, so some of the financial applications also use them. So at least in many cases, people want, if not fairness, like fair algorithms, but they also want fairness metrics. And currently, I think what has happened is that people are more interested in fairness metrics, which is like a first step before actually going to fair algorithms, but they want fairness metrics that are specific to their problems. Just to keep track of, so typically fairness is considered as a tax, in the sense that fairness brings down efficiency, or fairness brings down the accuracy or utility, because of which people don't want to sort of apply fairness constraints unless they are legally obligated to do so. So either it has to be a scenario where there is like a legal obligation to be fair, but in many of those circumstances also, people first of all want fairness evaluation, something that can help them evaluate and show that, oh, my model is fair. If there is a problem, we will fix it. Okay. And although there is like a other case that needs to be made, that fairness is good in the long run, because the data that you have, that itself is biased. So in fact, fairness constraints, one can show, so I did not talk about it, but we have other sets of results where we can show that applying fairness constraint is actually good, because what you have is not the true data distribution, but you have a biased data distribution. So if you maximize accuracy and then go to the actual data distribution, you might not be as good as if you apply fairness constraints. You might look worse on this biased data distribution, but when you deploy it on the true data distribution, you might actually be better. Yes.
an example of underprivileged
Uh-huh.
dual caste that
Uh-huh.
would bring home this message much more than women and men.
Sure. Although it can also be controversial.
That whole picture changes in that way.
No, but it's also controversial. There are also like representation constraints make sense, but there are, I think, one important direction which is underexplored is long-term fairness, where what you predict changes your data distribution, and so there is sort of a long-term chain, and then you want to basically care about fairness in the long run instead of fairness at the current step.
I understand how this is motivating randomness and how it helps them. But and sure, so say you have something like trees or some sort of decision trees or something, then it makes sense you have an ensemble.
Uh-huh.
But what happens when you're looking at deep learning?
Uh-huh.
How do you think of this there? Because in some sense, randomization is already there if you're using something like softmax.
Uh-huh.
On the second hand, you can't really afford to have an ensemble of deep learning models. So do you try to put this constraint in your law? So what kind of stuff do you think?
So typically there people would just look at some regularized, fairness regularized laws. Yes. Well,
I get. Also, to add into that, so
Uh.
I remember reading somewhere that for these fairness algorithms have been implemented for rationing and disasters. So when there's a natural disaster, they've actually been implemented in some states in the US, I forget. But because you want to ration fairly to whoever comes throughout the day, so given some assumption that if you can estimate how many people are coming, you actually can ration fairly to different types of people. These have been used there, and I think it's incentivized to be fair there.
Yes.
There's no fairness tax there.
Uh-huh.
I think that's beneficial.
Do people do some kind of benchmarking of fairness metrics, across companies and stuff?
Cross companies, no.
Yeah.
Although it would be good to have something like that. But what?
Company is the best for that.
But for what kind of things?
No, I said who are good in hiring kind of minority candidates.
You don't have the data, right? You have the data when it's someone.
So if you make it public, then you incentivize people more to behave better.
Some sort of a centralized benchmark or something.
Metrics instead, so you can.
Yeah, like other metrics are centralized that people use.
Okay.
They don't have any.